Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. Sit back and relax while we tweak weird and wonderful science in your brain. I'm Ian Woolf. On this edition, 20 years of bug bots. But first up, here's news about other cyborgs. Friendly on demand. Researchers at Northwestern University in Illinois in the USA have used a first-of-its-kind ultra-miniature wireless, battery-free and fully implantable device that uses light to activate neurons and force mice to make friends. The thin, flexible, wireless nature of the implant allows the mice to look normal and behave normally in realistic environments, so that researchers can observe them under more natural conditions. Previous studies had the animals wired up, and the optic fibres would get tangled or break, and it seemed unlikely the mice were interacting naturally with big wires trailing from their heads. Optogenetics is where genes which can be switched on and off by light are engineered into cells, so the characteristics can be precisely controlled with an implanted light. Optogenetics could someday be used to fix blindness or reverse paralysis. In this case, the mouse neurons were engineered with a light-sensitive gene from algae. The wireless implant is half a millimetre thick and sits beneath the skin on the outer surface of the mouse's skull. The implant has a filamentary probe fitted with light-emitting diodes that protrudes downwards into the brain through a tiny cranial defect. Researchers operate the light in real time using wireless near-field communication from a computer. The same NFC technology that you use to pay with your phone or tap-to-pay card. An antenna surrounding the animal's enclosure delivers power to the wireless device, eliminating the need for batteries. The mice with wireless implants were close together inside an enclosure, with the scientists using the implanted light to synchronously activate neurons in the brain region associated with higher-order executive function. The result was an increase in the frequency and duration of social interactions between the mice. Desynchronizing the light stimulation instantly decreased social interactions in the same pair of mice. They stopped being friends. In a group setting, researchers could make any chosen pair of mice interact more than the others. They could make them friendly on demand. The researchers want to study brain activity in complex, socially interacting groups of individuals, and to investigate how bonds form and break between individuals in these groups, and to examine how social hierarchies arise from these interactions. Their paper was titled Wireless Multilateral Devices for Optogenetic Studies of Individual and Social Behaviours, and was published in the journal Nature Neuroscience. Cyborg Venus flytraps. Researchers at Nanyang Technological University in Singapore have developed a device that can deliver electrical signals from and to plants, for communication and control. They call their conforming electrode attached by hydrogel a communication device. Naturally, they chose Venus flytraps to communicate with first. Venus flytraps normally close their traps when the trigger hairs in a trap have been touched a few times by insects getting a free meal of nectar from inside the leaf trap. The researchers attached a flexible electrode on the surface of a Venus flytrap plant using a soft and sticky hydrogel adhesive. With the electrode attached to the surface of the flytrap, researchers can achieve two things: pick up electrical signals to monitor how the plant responds to its environment, and transmit electrical signals to the plant to cause it to close the trap. Using a smartphone to transmit signals of electrical pulses to the device at a specific frequency, the team triggered the Venus flytrap to close its leaves on demand in 1.3 seconds. The researchers attached the Venus flytrap to a robot arm. and through the smartphone and the electrode, stimulated its leaf to close and pick up thin wires and moving objects. The researchers hope that when the technology matures, the robot plants may see applications in fruit harvesting. Backpackers beware. Results from a separate study, published in the scientific journal Advanced Materials, found that by using a type of hydrogel called thermogel, which gradually transforms from liquid to a stretchable gel at room temperature, they could attach their electrodes to a greater variety of plants with different surface textures, and achieve higher quality signal detection, despite plants moving and growing in response to the environment. The team hope that as well as learning about plant-based robots from the Venus flytraps, by reading electrical signals from crops, they will better pick up when plants are distressed from pests, disease or pollution, for more attentive agriculture. Researchers think that having sensors on numerous plants connected with miniaturized wireless circuits could allow the plants to be connected to the internet, forming an internet of plants to communicate with farmers. At this stage, we don't know what the Venus flytraps have to say about it. The paper was titled An On-Demand Plant-Based Actuator Created Using Conformable Electrodes and was published in the journal Nature Electronics. You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. 20 years of robo-roaches, from 2001 to the present day. Cockroaches to the rescue to find people buried in rubble after earthquakes. At least, that's the vision. I first reported on remote-controlled cockroach research in 2005, with a jolly giant Madagascan hissing cockroach empowered by driving a knee-high, three-wheeled vehicle wherever it chose. By 2011, things turned more sinister, with researchers cruelly controlling cockroaches with electric currents to their antennae to direct them. Here's my report from 2013 on the history of remote insect control, from cockroach Daleks to rescue roaches to rescue moths. Back in 2005, I reported how engineer and artist Garnet Hertz at the University of California, Irvine had developed a three-wheeled robot car that giant Madagascan hissing cockroaches could drive by walking on a ping-pong ball attached to a trackball. His aim was to show that an insect could drive a robot vehicle. 8 years later, in 2013, biomimicry engineers from the Research Center for Advanced Science and Technology at the University of Tokyo have done exactly the same thing, but with moths. Their aim is to have their moths drive robot cars to track things by lust. Sexy Daleks. The trackball works like a computer mouse. As the cockroach or moth walks, the ball spins and the three-wheeled cart moves in the direction the insect intended to go, only much faster and further. The cockroaches were given feedback to help them steer by a ring of lights that stopped them bumping into things. The giant Madagascan hissing cockroaches were merely given the ability to drive wherever they wanted. But building on that accomplishment, the Japanese moths have been put to work. But before we get to the details, have animals piloted vehicles before? Between 1983 and 1985, Mark Pauline, founder of Survivor Research Labs, had a four-legged walking machine piloted by a guinea pig. The guinea pig, named Stu, was trained to drive the machine by rewards of lettuce. Although Stu was trained to enjoy entering the robot, once he was inside, Stu tended to shift himself into a position that stopped the robot moving. There are videos on YouTube from the Broadway performance of all the surreal machines, but you don't see much of Stu. In 1997, Ken Ronaldo created a device driven by 4 Siamese fighting fish that could see each other from 4 separate bowls. The fish determined the direction and speed of robot motorised arms that held their bowl by crossing any of 6 light beams to move their fish tanks. This changed the fish's view of the world and location in space, but didn't let them kill their rival fish. So the fish would swim around in the bowl and the arm would move the bowl. The fish actually watched each other through the air between their bowls of water. Ken Rinaldo went on to develop a living tongue installation where an artificial stomach with live stomach bacteria controlled a giant robot tongue. When a human sits in the tongue chair, if the artificial stomach population of bacteria is happily breeding, then the human gets a massage from the tongue. I shudder to think what happens when the bacteria are unhappy. Male silk moths are famous for having what may be the most sensitive smelling system in the world, as long as that smell is a female silk moth in heat. The scientific name of the silk moth is Bombyx mori, and the female sex pheromone that the males follow is called bombicol. Back in Japan in 1995, the researchers recorded the signals from a male silk moth's antenna when it was detecting female sex pheromones. Then they attached the antenna to a robot and successfully steered the robot to the source of the scent by using the decoded electrical signals from the detached silk moth antennae. In 2010, this information was used to direct a moth that had electrodes attached to its antennae and which was lifted into the air by a helium balloon. The paper is titled Remote Control of a Cyborg Moth Using Nanotube-Enhanced Flexible Neuroprosthetic Probe. In 2013, moths were able to navigate their electric tricycle to a target location inside a wind tunnel. The Japanese scientists tested 14 male moths, which individually had to guide their robot vehicles towards female sex pheromone scents. They were so good at this that the researchers teased the moths by making things harder. Like a juggler replacing one of his juggling balls with a bowling ball, they needed to test the limits. To make things more difficult for the silk moths, they made one of the wheel's motors stronger than the others, giving the vehicle a turning bias that the moths had to overcome. Picture this. You try to move your robot vehicle towards the alluring scent of a female wafting through the wind tunnel, and you keep turning too far to the right. The moths still reached their sexy female moth-smelling target. The moths track chemical concentration from dilute to concentrated to track a few molecules as they get more numerous and stronger smelling all the way back to the source. For airborne chemicals, moths appear to use the strategy of surging upwards into the air and then zigzagging to pick up the scent molecules. Of course, they couldn't do this as naturally while strapped into the pilot chair of a wheeled vehicle. Perhaps in the future, the moths will be piloting winged flying robot insects like the ones recently developed at Harvard University, where the more natural flying strategies could be used. The Japanese engineers hope to turn the moth's attention to tracking the odours given off by industrial chemical leaks and spills, like a cyborg insect bloodhound. They aim to try and replicate what the moth's sensory motor system does in electronics, or, failing that, to simply keep harnessing the moths, like canaries in coal mines, if those canaries were attached to robotic vehicles that gave them the power to move towards a gas leak and snuff them out. Perhaps genetic engineering could make the moths turned on by scents more useful than silk moth girls gone wild. The paper published in the Bioinspiration and Biomimetics Journal of IOP Science from the Institute of Physics is titled Odour Tracking Capability of a Silk Moth Driving a Mobile Robot with Turning Bias and Time Delay. Garnet Hertz was directly inspired by the remote-controlled cockroach project of Professor Isao Shimayama at the University of Tokyo in 2001. Signals from a radio remote control were received by the cockroach's backpack computer and used to control the cockroach's movement by stimulating electrodes implanted in their antennae. With microphones and cameras, the cockroach became a remotely controlled bugged bug. Professor Shimayama had hopes of the remotely controlled cockroaches being used to find survivors in rubble after an earthquake. One of the bug cockroaches was depicted in the movie The Fifth Element. The American Defense Advanced Research Projects Agency, DARPA, also had remotely controlled rats with electrodes implanted in their brains. The rats felt artificially happy whenever they moved in the direction dictated by their handlers. Having the animals remotely control their own robots is a much more humane use of resources. Strangely, the Tokyo moth researchers don't mention Garnet Hertz's pioneering work at all in their paper, despite their insect-steered vehicle looking like a much smaller version of Hertz's insect-steered vehicle, and the videos of the moths driving look very reminiscent of the cockroaches driving. Perhaps it's because Hertz's work was labelled an art project. I hope the Japanese haven't reinvented the insect-controlled wheel. Still in 2013, in America, things turned crueler, as the Backyard Brains company marketed a cockroach neurosurgery kit, where you could modify a house cockroach into a remote-controlled insect as a learning project. At Dorkbot, I interviewed an engineer who'd bought the kit and built the project. Remember the remote-controlled cockroaches? Now they're available in kit form. Manuel Betancourt is an engineer who develops software for mobile phones. He's been making cockroach and cricket legs twitch to music for Dorkbot, based on projects sold by Backyard Brains, an American company that makes neuroscience project kits. So Manuel, we're here at Dorkbot, and you've got a project involving electricity and cockroach legs.
Yes, it's a pretty interesting project from some neuroscience guys from the US. So I work a lot with different neurofeedback devices, electroencephalogram, electrocardiograms. I'm actually an electronics engineer, but I work developing software for mobiles, iPhone, Android. So I did this project with these friends from the US that is to measure the action potential of the neurons in the cockroach leg. So you can connect two electrodes to the leg and then see the response on real time. And then you can feed it electricity and it will move. You can put some music, it will move. Right now they have a very nice project that is a controlled remote cockroach. Will be my next experiment. So you put the two electrodes on the actual antennas of the cockroach. So you can make it turn left, right. So I am looking forward into integrating that with some robotics and a little bit of an artist experiment.
So your current project with the cockroach legs, or your recent project, did that involve the legs still being on the cockroaches?
No, you have to take the leg off the cockroach. Like maybe you have 4 hours that all the neurons in the leg are still alive. After that, they start degrading. But basically, you have to rip off the leg, and like some people get sad, but like the leg might grow again for cockroach, for crickets. But you have so much cockroaches here in Sydney that I think it's not a big problem.
Do you have any videos of this work that people could see online? Are there any recordings?
Definitely. The official site is Backyard Science. So you can go to backyardscience.com and see all the experiments with the cockroaches. And this is basically neuroscience experiments that run for tens of thousands of dollars. But this group made it so cheap, open source, and you can basically do an experiment that costs tens of thousands of dollars for $100.
That's amazing. So they go to backyardscience.com to look at what you've done. And what about the upcoming project with the remote control cockroach?
Oh, is there as well?
It's there as well?
Yes.
Awesome. Well, Manuel, thank you very much.
Thank you very much. Glad to meet you.
That was Manuel Betancourt. And yes, cockroaches can grow their legs back when they next molt their exoskeleton to grow a new one, unless they're too old for any new molts.
Confidentially, I think the idea indubitably has questionable sociological ramifications.
Robo-roach swarms in 2020. Digital Nature Group at the University of Tsukuba in Japan is working towards a post-ubiquitous computing era consisting of seamless combination of computational resources and non-computational resources, by which they mean an army of cyborg cockroaches living in your house, appearing out of nowhere, fulfilling their tasks, and then hiding again. To your standard cockroach remotely controlled by a wireless backpack sending signals to its antennae, they add wireless connectivity. some points of reference markers, an overhead camera system to produce a resilient swarm of remote control cockroaches that can collaborate on tasks. The researchers suggest that the swarm could be used as a display by making each cockroach into a pixel to transport objects or to draw things. The researchers say the reason to use cockroaches is that you can take advantage of their impressive ruggedness, efficiency, high power to weight ratio, and mobility. They can feed themselves, meaning that whenever you don't need the swarm to perform some task for you, you can deactivate the control system and let them scurry off to find crumbs in dark places, until you once again compel them to assemble for work. They call them calm bots. Very relaxing. And in 2021, a team led by researchers at Nanyang Technological University of Singapore attached a minimal set of sensors and processing units to the back of a giant Madagascan hissing cockroach. Their 5.5 gram backpack contains a Texas Instruments microcontroller, an infrared camera, Bluetooth transceiver, carbon dioxide sensor, temperature and humidity sensor, and an inertial measurement unit with 2 megabytes of flash memory to record activities during operations. The battery lasts for over 2 hours. Giant Madagascar hissing cockroaches can carry 15 grams, so a 5.5 gram backpack is no problem for them. The infrared camera, coupled with a machine learning algorithm, is capable of locating humans. To direct the insect's flight path, and these are flying cockroaches, the team attached electrodes from the backpack to the cockroach's cerci to provide electrical stimulation. Cerci are small sensory organs at the cockroach's rear end that have a priority override to the cockroach's brain to help it run away from danger. Whenever a cockroach feels a presence with its cerci, its legs start running, even before the brain receives the signal. When the left cercis is stimulated, the insect will fly to the right, and when the right cercis is stimulated, the insect will fly to the left. This is an upgrade to previous technology which electrically stimulated cockroaches' antennae to direct its movement. The cyborg insects had a success rate of 94% when directed to waypoints in a simulated disaster scene in a lab. Using the infrared camera with software, the team could discern humans from non-human objects with an 87% average accuracy. They hope to add real-time position tracking to make it even easier to find people. The paper was titled Insect-Computer Hybrid System for Autonomous Search and Rescue Mission and was published as a preprint. This project marks 20 years of cybernetic cockroach research in the service of saving people from collapsed buildings after an earthquake. Please check the show notes webpage for videos and links for all the cyber roaches, moths and plants. I found a lot of videos.
When the moon shall have faded from the sky, and the sun shall shine at noonday a dull cherry red, and the ice cap shall have crept downward to the equator from either pole, when all cities shall have long been dead, and all life shall be on the very verge of extinction on the globe, then on a bit of lichen growing on the bald rocks beside the eternal snows of Panama shall be seated a tiny insect preening its antennae in the glow of the worn-out sun, representing the sole survivor of animal life in this our earth, a melancholy bug. It could happen. After all, the odds favor the bug over man by at least 500,000 to 1.
For instance, the descendants of one pair of houseflies during the 6 months of one spring and summer would number 191 million if all of them lived and reproduced normally. That's equivalent to a layer of flies 4.5 feet deep and 300 flies to the cubic inch, covering the entire United States. But only a minute fraction of them survive.
And that's all from us this week on Diffusion. Are you a scientist, artist, biohacker or maker who'd like to be interviewed about your work? Would your company like to sponsor Diffusion? Send your contributions, opinions, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com. Please like the Diffusion Science Radio page on Facebook and rate the show on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. The news music was Rhinos theme by Kevin MacLeod of Incompetech.com. I produce Diffusion, which is broadcast around Australia to 28 stations on the Community Radio Network, including Radio Blue Mountains 89.1 FM in New South Wales, 8CCC in Alice Springs and Tennant Creek, 2MVR in Nambucca Valley, 3MBR in the Mallee Border districts of Victoria and South Australia, City Park Radio 7LTN in Launceston, Tasmania, and 2XXFM in Canberra. Diffusion is narrowcast on Indigo FM 88 in northeast Victoria. Diffusion is syndicated globally on astronomy.fm. Subscribe to the podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos, and so many videos about this week's show. If you enjoyed this show, you can explore more than 1,000 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Make a donation through paypal.me/Ian Woolf, or join my patrons at patreon.com/diffusionradio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits. Photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.